In this video, I'm going to talk about inductive coupling. Whenever a current exists, it produces a magnetic flux proportional to the current. If I have a wire here with current I, I'm going to produce a magnetic flux that wraps around the wire according to the right-hand rule, and that's the magnetic flux. A magnetic flux for that wire is equal to the inductance, which is the self-inductance times current. That's equal to the magnetic flux. Now let's say I have that circuit, that wire, we're going to call that I1, and here it is again, I1, in the presence of another circuit, a second circuit 2. So here's circuit 1, here's circuit 2. That current is going to cause a magnetic flux again, but this time that magnetic flux is going to penetrate this current loop here. I'm showing it coming around the back side and loop around because that's what the magnetic field has to do. And what we have is a certain amount of flux that is contained within the area defined by this current loop. That flux, phi sub 1, 2, the flux from circuit 1 in circuit 2 is equal to M times I, where M is the mutual inductance. And let me make a side note here. You'll often see B here, which is the magnetic flux density, and that's just phi divided by A. So in this case, it would be the net amount of magnetic flux penetrating area A divided by area A, and that's the magnetic flux density. We know by Maxwell's equations that the voltage, here the voltage, has to equal the time derivative of the net magnetic flux through that area. And so you can see V equals negative d dt times the area integral times the magnetic flux density times the area. And I want you to remember, you may remember this equation. You've probably seen that somewhere. V equals L di dt. There's the inductance, the self-inductance, and there's an analogous equation, V equals M di dt, where M is the mutual inductance. We know that, oh, look at this. This is voltage, and this is voltage. And that's going to be the voltage here induced in the current loop. Let's set these equal to each other. V equals negative d dt times the integral of the magnetic flux density times the area, and that's going to equal M times di dt, where this is I1. So we're talking about the voltage in the current loop, which is induced by the current in I1. Let me scroll down. Now, you don't want in the circuit, let's say you've designed this circuit and you really don't want that noise coupling into this loop over here. That wasn't intentional. You want to reduce that voltage. The levers you have for reducing that voltage are reducing the magnetic flux density here, reducing the area here, reducing the frequency of the oscillation of current 1 here, d dt, or reducing that current in circuit 1. In practice, you really don't have any control over this or this because you may not know where they're coming from. You may not know what they are. The only things you can have control over are the magnetic flux density and the area. And there are only a few things you can do to decrease these quantities. For the magnetic flux density, you can separate these two circuits. So separate circuit 2 from circuit 1, put circuit 2 way over here, way away from another circuit that you suspect may be noisy. Another thing is to put your conductors very close to ground so there's not a lot of area to couple. So instead of having maybe your copper trace here and your ground plane down here, you have, and there's some distance d, you put them, you pick a process where they're much closer together, d prime. If you're providing cabling to your printed circuit board, if you're in a lab type situation, you would want to twist the wires together, and I have covered that in another video.